Alright, welcome back to our second video on 6.9, Quantifier Rules with Relations, and this is our second video there. So we just finished in the previous video talking about a demonstration that from the fact that R is an asymmetric relation, we can syntactically deduce that R is an irreflexive relation. It's important to note that when I or a professor says something like all asymmetric relations are irreflexive, that does not mean, okay, that all irreflexive relations are asymmetric, okay? Those are two different statements as you should be well aware of now at this point in the course, right? To say if P then Q is not to thereby assert that if Q then P. So, can an irreflexive relation be symmetric? We might pose that as an open question. In other words, could we have this be true and this be true? Is that consistent? And it is indeed consistent, and a relation can be irreflexive and symmetric. So just because all asymmetric relations are irreflexive, it does not thereby follow that all irreflexive relations are asymmetric, and indeed that's not true. It is possible to have an irreflexive and symmetric relation. Can you produce, going into the well a little bit, going back to chapter 5 and tableau techniques, an interpretation according to which this statement, the relation R is both irreflexive and symmetric, is true, and maybe just use a couple of objects to illustrate the point to yourself. Pause now. Okay, so here's an interpretation where the relation R is both irreflexive and symmetric. So this would be your technique when you're asking questions like this. Can I produce an interpretation that illustrates it to me, or can I do the syntactic deduction if I want to prove, for example, that an asymmetric relation is irreflexive? So in this case, can we have irreflexive and symmetric? And if you tried to say it's irreflexive, therefore it's not symmetric or something like that, you wouldn't be able to produce the syntactic deduction, which means maybe you should think about, hey, can I do an interpretation where both are true? So in this case you can. Notice RAA and RBB are both false, so this is in two objects, and therefore it's true that everything is such that it does not bear R to itself, namely both A and B, and A bears R to B and B bears R to A, therefore it's a symmetric relationship. And so this sort of shows that a relation, at least from a purely logical point of view, can be both irreflexive and symmetric. So it's important to note that. Okay, let's continue on with our syntactic deduction examples. So let's practice this one, and this shows us another interesting result that we discussed in chapter 4 but did not have the resources to sort of prove analytically, but we do now, and that is that if a relation is both transitive, right, if Rxy and Ryz, then Rxz, and it's irreflexive. So if it has these two features, the relation R is this way, and it's also such that it's irreflexive, then it is going to be asymmetric on the condition that it's both of these, it's asymmetric. And you're going to be able to syntactically deduce that. Now, let's go ahead and start this one off by reverse engineering the conclusion. That is to say, pretend you have it available and strip it of its quantifiers and look at what it might look like independently of having any quantifiers attached to it, because that's going to tell you what you're going to try to build from premises 1 and 2 here. So pause now, reverse engineer the conclusion. Okay, so if you had the conclusion, you would strip off, the quantifiers, and you're not 100% sure exactly what you're looking for here, but you know that you're going to need an x and a y in your conclusion, and so it makes sense to universally instantiate to just different things, meaning RU and RU1. Those are different, to sort of mark the x and the y out for yourself so you know how to build the conclusion properly. But yeah, so you strip off the x and we'll just go to u, and then we'll strip off the y and we'll go to u1, and you're left with this. And it's like, okay, aha, now I have an insight for how to solve this problem. I could start with an assumption, okay? I could assume RU1 and then look for it's not the case that RU1U, right? And if I still couldn't get that, I could do a possible IP assumption nested within that, and that's exactly what we're going to do. Of course, you might have come up with a different way of solving the problem, and that's fine as well. This is just a helpful aid which you may use or not use as you see fit. But with that sort of hint in place that we're looking at a possible CP situation here, go ahead and see if you can't produce the syntactic deduction from these two premises that this is indeed true. Pause now. Okay, if you were able to get it, that's great. If not, I'm going to sort of walk you through a process here with some hints along the way so you can try to figure it out. But what I want you to do now is I want you to say, okay, I'm going to assume this and try to demonstrate that based on this assumption. So just do that line right now. See if you can figure out, what would my assumption be and what would I be looking for if I were to make this assumption. Okay, try that for line 3. Pause now. Okay, so we're going to assume this, which is the antecedent here, and we're going to look for the consequent, and that's what we're going to be looking for. Now let's assume, just for the sake of argument, that we were stuck here. So we're going to make another assumption. That is, we were going to nest an IP assumption. So now we're going to assume the negation of what we're looking for, and what we're looking for in this case right now is this guy. So what would your assumption look like now, and then what would you be looking for after you make that newest assumption? Go ahead and do that for line 4 right here. Pause now. Okay, so on this strategy, we would assume the negation of what we were looking for, and what we were looking for was this guy, so the negation of it is this, and now, of course, we're looking for a contradiction. So, using these materials, 3, 4, plus your premises up here, can you find anything of the form P and not P? Anything of that form will do. Pause now and see if you can't figure out a contradiction from 3, 4, and 1 and 2. So the key to figuring this out, and it's a little bit involved, is to sort of combine 1 and 2 together, and to use them together in such a way that you can produce the contradiction. So the way I did it here was, first of all, I got rid of the pesky double negation here, and so that left me with RU1 and RU. And notice here in 3 I have RU, RU1. So these are kind of like the reverses of each other, right? This is RU, U1, this is RU1, U, and that speaks to the transitivity sort of idea here in the first premise. So if you can imagine this as RU, RU1, and this is RU1, RU. Okay, that's the real key. Then you can start thinking about how to apply this and how to apply that. So instantiating the first premise, right, to RU, pulling off the X, and to RU1, pulling off the Y, and then pulling off the Z, going back to RU, right, and where the key idea is to be able to apply the second premise, we get this construction, and of course modus ponens on that is ready from 6, and that yields RUU. But since we have the irreflexivity clause as a premise in 2, we can of course invoke it's not the case that RUU yielding our contradiction. So pretty complex situation, but ultimately a very nice demonstration that in fact from transitive and irreflexive you can deduce asymmetric. Really nice idea. So having obtained what we wanted from this assumption, P and not P, we've got something of the form P and not P here. We discharge this assumption. So in line 13, we write down the first thing we assumed here in 4, arrow, the last thing we got here in 12, and that's that. And then how do we follow up all of our indirect proofs in the routine in our present text? How is that done? It's all the same as before. See if you can figure out how to finish off the RUU and not RUU aspect of this problem here. Pause now. Well, since this here in 13 logically implies a contradiction, and we know contradictions are not allowed, they're prohibited by the axiom law of non-contradiction, we can set up a modus tollens, which after double negating cleaning up leads us straight to not the case that RU1U, which is exactly what we wanted from our as yet undischarged first assumption. Okay, and so we've got that here, and so we discharge that assumption now, and we write down the first thing we assumed, the last thing we got, and this is a perfect construction for what we're looking for, right? And so after that, it's just a matter of building the desired conclusion. And so there's one last step in here. Can you go ahead and finish it off by yourself? What would it be? Perfect. And so this is what your final product would look like, and this is the demonstration that from transitivity and irreflexivity, you're guaranteed asymmetry. Pretty nifty result. And it's just wonderful that you're actually in a position, not just for someone to tell you, hey, if you're transitive and you're irreflexive, then you're asymmetric, but you can actually, and this wasn't the only way to do it, you can actually work out the syntactic deduction now. And so this gave us a lot of practice the way I did it here with, CP with relations and IP nested within it and how all of that works. And you can see it just follows the same model as the propositional case and with just property constants and things of that nature. Okay, let's look at one more final case, and this is kind of something that you pick up on in chapters 4 and 5, but now we're in a position for you to be able to prove some of your intuitions are accurate, and that's if, can we reverse the order of the quantifiers in a relational sentence, provided we also reverse the order of the relata. And if you have the intuition that you can in certain cases, you might want to check out whether or not from the one you can logically deduce the other and vice versa. And so let's look at an example of that here. Go ahead and see if you can't syntactically deduce this conclusion from this premise. And if you need to, go ahead and, reverse engineer this and picture it stripped of quantifiers and what it would look like. And that's what you would be building to from your premise. Okay, or otherwise just solve it any way you can. Pause now and see if you can't syntactically deduce this conclusion from this one and only premise. Okay, hopefully you were able to get it, but you start with your premise. You're going to strip off the universal quantifier, and that's going to leave you with a U here, EY, RUV, and then it's just a matter of building the thing that you want correctly. So remember, you're going to have to build this quantifier first and then this quantifier. So this one first and then this one, because they are rules of inference and not replacement, and you want to make sure you're putting them in the appropriate places based on where the relata are. All right, logic fans, good job. Be sure you're checking out the text, talking to your professor, practicing tons of problems and all the solutions available for you so you can really iron out the kinks in your problem-solving strategies and get these important notions down. We'll see you on the next video.